Hey everyone, and welcome to this explainer. Today, we're taking a deep dive into the hidden forces that literally power our modern world. We're going to be decoding Ohm's law, and by the end of this session, you'll see exactly how invisible electricity is measured, calculated, and perfectly balanced. Let's get into it. So, how does a simple wire control invisible energy? Honestly, it's a completely fascinating puzzle. Think about it for a second. How do engineers safely tame raw, powerful electrical energy so it can toast your bread, charge up your smartphone, or run a massive industrial machine without just instantly blowing it to pieces? Well, it all comes down to a set of incredibly precise, beautifully proportional relationships. Here's our roadmap for today. 1. The water pipe analogy. 2. Defining Ohm's law. 3. Resistance and electrical power. 4. The Ohm's law experiment. And finally, 5. When Ohm's law fails.
All right, let's jump straight into Section 1, the water pipe analogy. Because electrons are literally invisible to the human eye, wrapping your head around how they move through a circuit can feel kind of abstract. So to really understand invisible electricity, we need a solid mental model. And it's amazing how perfectly a mechanical water system maps onto an electrical one. Imagine water flowing through a giant system of pipes. In our electrical circuit, voltage is exactly like water pressure. It's the physical force pushing the charge along. Current? Well, that's the water flow itself, the actual volume of water moving through the pipe at any given moment. And finally, resistance is the size of the pipe. If you have a massive amount of water pressure or voltage, it's going to push a lot of water. But if you suddenly make that pipe incredibly narrow, you're increasing the resistance. And that strictly limits how much water can flow through, completely regardless of how high the pressure is.
Which brings us to Section 2, defining Ohm's law. The really crucial thing here is that pressure, flow, and pipe size are locked in this permanent balancing act. When we translate our water pipe analogy into the official mathematical rule of electricity, we get Ohm's law. Discovered by German physicist George Simon Ohm way back in the 19th century, the law states, the current flowing through a conductor is directly proportional to the potential difference, or voltage, across it, provided temperature remains constant. Now, I want you to mentally highlight that very last phrase for me, provided temperature remains constant. That is a massive caveat, and we are absolutely going to come back to it later in this explainer. To make this math incredibly intuitive, we use what's known as the magic triangle. This brilliantly illustrates how you can solve for any single one of these variables if you just know the other two. Say you need to find voltage. It's simply current multiplied by resistance. Need to find current. That's voltage divided by resistance. Want to know the resistance? Just divide the voltage by the current. It's just a wildly elegant, simple mathematical relationship. Let's connect this right back to our water pipe analogy to really solidify this relationship. If you double the water pressure, meaning the voltage, you are going to push exactly twice as much water through that pipe, doubling the current. Make sense? But if you double the resistance by swapping in a pipe that's half as wide, you are going to strictly cut that current in half. They scale together in absolute perfect harmony. Okay, moving on to Section 3, resistance and electrical power. Let's shift focus for a second. What exactly causes this resistance in the real world? Before we can calculate the total electrical power doing the actual physical work in our devices, we really have to understand resistance. The standard unit for resistance is the ohm, which is represented by the Greek letter omega. And resistance isn't just some random number pulled out of thin air. It is strictly dictated by physical reality. Think about a physical wire. The length of the conductor matters. A longer wire inherently has more resistance. The cross-sectional area matters. A thicker wire has less resistance, just like our wider water pipe. The material itself matters. Copper allows electrons to flow beautifully, while something like rubber stops them cold. And finally, temperature heavily impacts resistance because the atomic vibrations from heat actually scatter the flowing charges. Now, when electricity successfully overcomes that resistance, the energy is converted into heat or mechanical energy. We call this electrical power, and it's measured in watts. What's so amazing here is that we can easily calculate this power just by substituting our Ohm's law variables. Power equals voltage times current. Or, depending on what variables you actually have on hand, you can use power equals voltage squared divided by resistance, or power equals current squared times resistance. Let's put this into perspective with a quick real-world example to build some momentum. Picture an everyday electric iron. You know the resistance of the iron's heating element is exactly 50 ohms, and it draws a current of 3.2 amps.
So how much voltage is required to actually make this iron work? Using our formula, voltage equals current times resistance, we just multiply 3.2 amps by 50 ohms. And that gives us exactly 160 volts. That is the precise electrical pressure needed to push that specific current through that specific iron.
All right, section 4, the Ohm's Law experiment. We've done the math on paper, right? But science demands actual physical proof. If you were to jump into a lab right now to prove this math in the real world, you'd grab a battery, an ammeter to measure current, a voltmeter for voltage, and a variable resistor, which is called a rheostat. Then you'd follow 4 crisp, actionable steps. First, close the circuit and gradually slide the terminal on the rheostat to increase the current. As you make each tiny little movement, record the corresponding voltage and current. Finally, calculate the ratio by dividing the voltage by the current for every single measurement. And what you'll find is pretty cool. The ratio is always the exact same number. That constant, that's your resistance. If you plot those numbers on a graph, they form a perfectly straight, linear diagonal line every time.
And that leads us to section 5, when Ohm's law fails.
Now that we deeply understand the rule, we've got to look at exactly where the rule completely breaks down. Ohm's law is brilliant for sure, but it's not infallible. We have to clearly separate materials into 2 distinct categories. Ohmic conductors, like copper and aluminum, obey Ohm's law perfectly. Their voltage to current graph is that perfectly straight line we just talked about. But non-ohmic conductors, like semiconductors, have a totally nonlinear curving graph. This tells us something absolutely vital. Ohm's law is empirical. It's based entirely on observing certain materials. It is not some unavoidable universal law of physics like gravity.
So where specifically does it fail? Well, there are a few major exceptions. Unilateral elements like diodes and transistors flat out break the rule because they only allow electric current to flow in one single direction. Furthermore, remember earlier when I asked you to mentally highlight provided temperature remains constant? A classic incandescent light bulb filament completely violates Ohm's law. As the current increases, the filament heats up brilliantly, which is why it glows. But that massive heat drastically changes its resistance in real time. It completely shatters the constant temperature requirement.
Which brings us to a pretty provocative final thought for today's explainer. We literally just learned that semiconductors are non-ohmic. They completely break Ohm's law. Yet the smartphone sitting in your pocket, the computer you're using right now, they all absolutely rely on those exact semiconductors to function. So, if the basic foundational mathematical rule of electricity doesn't even apply to the most critical components of our modern digital era, how on earth do engineers actually tame and control this nonlinear electricity? It is a fascinating mystery, and it's exactly the kind of complex puzzle I can't wait to explore with you next time. Thanks so much for joining me today to decode Ohm's law. See you in the next one.